Okay guys, welcome back to my lecture, Mechanical Behavior of Materials, course number 315008. I'm Klaus-Dieter in the spring semester 2022, and today I'm in the beautiful lab of Professor Megumi Kawasaki at Oregon State University. This is where I spent some time while I cannot get back to China. Today's lesson will be the introduction into the theory of fracture. As we look to the course topics, we are now here. We have finished just the dislocation theory last week and starting the semester with the introduction to the mechanical behavior, the elements of elasticity, then also the same in curved linear coordinates, theory of plasticity, the yield criteria, and then we had a few weeks on dislocation theory. There are still 5 other chapters left in the syllabus, namely fracture theory, what we start today, Weber statistics, that's also about fracturing, breaking, failure. And then we come to fatigue, this is cyclic deformation, and eventually you also get fracture and failure. Subsequently, we get creep. So creep is a relative important topic I want to emphasize in this course on. Thin films, and that's about it. So if we look now to the remaining lessons we have, today we are here on a Thursday. Then we have, including today, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 more lessons divided by 2 gives about 6 weeks we have. Out of the 13 weeks, so we are now 1 week over the mid of the course. We have 6 weeks remaining and we have 5 topics. And you will see the presentation of today has about 100 slides, maybe 95 slides, something like that. So I have to get a quick run through some of the topics, namely fracture theory, Weber statistics, because I also want to spend time on fatigue and creep, which are hot topics in research. And as we are material scientists, not so much mechanics people, we want to understand the physics, what's happening inside the material. And also thin films. I will see how much time I have to talk about the thin films, but at least we should have 1 week for it. So we have 5 topics, 6 weeks. I'm sure we're running out of time, so I have to hurry and cannot go into detail of each of them. The literature on fracture mechanics is shown here. We have the books by Brian Lawn and also Richard Herzberg. Herzberg is important literature which I recommend. Recently, I also found this book on fracture mechanics by T.L. Anderson. So this is a modern textbook. This 4th edition, I think, is by came out in 2017, so it's a relatively recent and more consistent presentations than what I will give you. You know already my slides, they are based on the Technion slides, great thanks to that, but as we will see, the inconsistencies in the formulas, you have seen already in the past for the shear modulus, we use the character or the formula sign G, uppercase G, or lowercase mu, the Greek character mu. So if you want to more consistent, we go to one textbook. But anyway, life is as it is, and it will be more confusing as you proceed in academics, because as you proceed, there will be more and more literature distributed over the subject of research you're looking into, and different people use different formula units. And, well, actually just today, I looked up. Google is always a good start to look up things to refresh things if you don't know them or you want to get a reminder. And I found this literature on crack control. I haven't read it, but it is using fracture theory to create tough new materials. So it resumes a little bit about the past, about what I will teach you today, textbook knowledge. Not so much teaching, also discussing textbook knowledge, but then how to apply that to create tough new materials. There's a DOI. If you're interested in it, look it up. If you have a Technion account, you can download it through the Science Online Library. Okay, let's get started here. This looks very much like at the beginning when we started to look to the theoretical strengths under shear. And we do the same now, looking to theoretical strengths under tension in the atomic potential. And you remember we have approximated this behavior. So we have a strong force and then we have a not so strong force as we go far away. So we have to overcome a strong stress here, which increases with displacement x or u we had in the past strongly, but then as you go over a certain maximum, then it decreases again because of these attractive and repulsive forces and potentials we have. Okay, so we know already what happens in the potential landscape when we pull atoms apart. We first linear increase to a maximum and then decrease again, and we can this maximum we can, for example, approximate by a sine function. So sigma equals some sigma t here, the maximum, times sine of pi times x over x star, where x star is this, and you know when x over x star becomes pi, then it goes back to 0. So that describes well the slope at 0, so at x equals 0 for small strains, and that's what we're talking about, small strains, small displacements, x, and the slope is then, of course, dx, d sigma over dx. So that's the schematics. I've discussed that already. And we assume, here it's written again, so sigma equals a sigma top times sine pi x over x star, where x star is this virtual point there. And assume Hooke's law for the small deformation and tension. So sigma equals elasticity modulus times epsilon. And the displacement strain relationship, so epsilon is delta x, so it's already a delta variant here, du over dx. That's in general coordinates. So our x here, it's x, it's a change of the displacement divided by the atomic distance, a0. So this is x and this is a0. And back to Hooke's law, sigma equals x over a0. Then we get the sigma x relationship for small deformation, which is this sine function. We can Taylor expand into the argument, and then we get sigma equals sigma t times pi over x star times x. So just the argument here replaces the sine just by the argument of the sine. And then we compare the stresses here and this one, sigma and sigma, and become sigma t pi over b x equals e x over a0. Or we can also make an assumption that x star is approximately of the order of magnitude of a0, and then sigma t reduces to e over pi. So that is the theoretical strength in the tensile experiment when we look to the atomic potentials and atomic forces. So, again, a table. We have glass. We have A zeros here, 10 to minus 10 meters. Approximately 3 times 10 to minus 10. Steels, they're all a few angstroms, 3 angstroms. Piano wire is also steel. Silicon, maybe 5 times 10 to minus 10 meters. So in an angstrom regime is the I0. Then we have E in gigapascal are the numbers. It varies between 60 and 495, so 500. Then we have sigma theoretical. In gigapascal gives those numbers. So between 14 and we see it up to 70 here in alumina visca, 45, so many tens of gigapascal. And the experimental strength in megapascal, it's often less than 1 gigapascal. Sometimes here we have 13 gigapascal for the iron visca. We know the viscas, they're very strong, of 15 megapascal. The silica fiber, also very thin fibers, 25 megapascal. But still, there is a lot of discrepancy to the theoretical strength. So why? We have an excellent model which fails to predict the strength of the engineering materials by approximately 2 orders of magnitude. So up to 1 to 2 orders of magnitude in most of the cases. So why such a nice model and we cannot predict? This is because we know before we had dislocations, and now we say there's no dislocations. We have the presence of cracks. This is for brittle material. Dislocations is for ductile material, and here we have for brittle material. So what is the weak point in the brittle material? The presence of cracks. There are always some inclusions, some distortions. So, if we have a distortion or hole or precipitate, let's say we have a hole here. We have done these calculations in the section of theory of elasticity. And we know we get stress concentration. At the border of the hole, so at the surface, at the boundary, we get 3 times the stress at infinity. If we apply a stress at infinity, S sigma infinity, S infinity, it amplifies to 3 times at the surface radius of the hole here. So 1 radius away, 2 radii, 1 diameter away, which is 2 radii away, it becomes lower and lower. And we remember these formulas, you can look them up. We have the sigma RR, we have, which is sigma infinity half, 1 minus A over R squared. So A is the radius of the inclusion. Here you see the image, and plus these cosine terms. So you can look the total the stresses, they become up to 3 times the stress applied at the infinity. This is stress concentration. So if it doesn't yield at infinity because I concentrate it, it becomes higher. Now, based on this, Inglis, so this guy C.E. Inglis, the author, has made this model in 1913 by describing a crack as an elongated ellipse. And the ellipse has some radius here. So radius of curvature, like if I make it spherical with the smallest radius of curvature here, then I get the highest stress concentration. This is when I make the A, it scales with A over R. So I get the highest stress concentration at this point where the radius is smallest. And then we can write down this solution for a plate with the elliptical slit. He wrote down this in 1913. So I have an opening of 2C, the crack, there's a crack in the material, 2C long, and 2B high, wide. So that's the crack opening. 2B, it's an ellipse with the two axes. The long axis or the half axis is C in the horizontal direction, in the longitudinal direction, and B, the half axis, so to say the radius, in the vertical, along Y. And Y is where we apply the stress, sigma A, sigma applied. And I mentioned the radius of curvature here in this corner. This is where it is largest, and where it's largest we have the highest stress concentration. So we can describe an ellipse like this, x squared over a squared plus y squared over b squared equals 1, or solve it to y, then becomes this formula. And then we can calculate in curve theory, linear algebra, you can calculate the curvature here, which turns out 1 over rho, the curvature, well, the curvature is 1 over rho, equals y double prime divided by 1 plus y prime squared to the 3/2. This is mathematics on the ellipse. And you can then resolve that the curvature of the radius of curvature equals b squared over a. So we have, and I have to say, a equals c. It's synonymous. Some formulas, they're copied with a, and some diagrams, they have a c here. So a and c in the next few slides, it's the same thing. So b squared over a, or b squared over c. And then with this sigma max, we can put it in and get this equation. So 2 square root a over rho, a over b, a over b, which is approximately, if rho is much smaller than a, then you can neglect the 1 against a over rho, because then a over rho becomes large, and the square root also becomes large compared to the 1. Then it gets this approximation. But if it's not so, then you take the first part, the correct part of the formula. So I wrote it down again here with a c. So c over b, here's a over b, and square root a over rho, square root c over rho. Because a is identical to c, just two different formula units for the same thing. Because these slides are mixed. I copy that here again. So let's say now c equals 3 times b. Put c equals, or a equals 3 times b here. Then we have b, 3b over b. This gives a 6, plus 1 is 7. So sigma max over sigma becomes 7. If we have here the situation, we have the ellipse, we have here the maximum curvature, which is one of the curvature radius, so minimum curvature radius there. And if we apply the stress in the y direction, then the sigma c critical, or sigma max, becomes 7. So the 6 plus 1. 6 times through the stress concentration, and 1 times through the applied stress. And this is the sigma yy. Also we have sigma xx, it's in this direction here, in the horizontal direction, the normal stress. Also concentrates a little bit, but not so dramatic. Of course, if you pull in the vertical direction, then the vertical stresses become larger. And we can imagine this, yeah? We spread the material, and the longer the crack is, the more lever arm we have to the point of the crack tip. We call this the crack tip here, where the rho is minimal. So the long axis of the ellipse is the crack tip. And the larger the 2a is, the more the lever arm I have, and the more concentration of stress I get. So this makes sense physically. I repeat that here again. So the stress concentration by the half-axis A or C is shown here again, that the sigma max equals sigma infinity times 1 plus 2 square root A over rho. Or if we express it in A and B, so not in A and rho, but in A and B, then we have the formula here to the top. Because rho, you also may want to remember this, is B square over A. And here I have the same formula, just replace A by C, because sometimes we use the C. So this is English solution. He formulated that in 1913. Sigma max over sigma is 1 plus 2a over b. So the question is, can it serve as a tool to predict fracture? Now let's take a small crack. A is 100 micrometer, so this is 100 micrometer, and B is 1 micrometer, so A over B is 1 over 100. And I can put that gives 2 times 1 over 100 plus 1 gives 201. So we have a huge stress concentration. But also we can now say A can be 100 millimeter and B just 1 millimeter. Then we have the same A over B ratio. And if we make a giant ellipse of 100 meter length A and spacing B 1 meter, then we still have the same aspect ratio, A over B. So this is the stresses, they are the same. If I have a big ellipse, a medium-sized ellipse, or a small ellipse, so the stresses around an elliptical hole in a stretched Hookean sheet remains the same as the hole size changes. But the stored elastic energy does not change. So there's different stored elastic energy because the stress field in a big ellipse is much larger than in a small ellipse. The release of that stress field and the stress energy can make much more damage than in the small. So that's why it would not scale in an experiment with just the A over B. So therefore we have to consider a different theory, and there Griffith, A. Griffith, of the Royal Aircraft Establishment came into the play. So he did experiments of bursting tests, bursting balls. So he took these balls, glass spheres, like Christmas balls, inside hollow, just the spheres, and he scratched them. He scratched them with different lengths and depths of scratches, so that he could test when they shatter under compressing them. He did it with balls and he did it with pipes. So he had spherical bulbs, like a light bulb, yeah, and he had circular tubes, elongated tubes, something like that, a light tube. lab, yeah? And 2c is the length of the crack. Q and R are the calculated principal stresses. So we have the Q and the R, the principal stresses, perpendicular and parallel to the crack. So Q is parallel to the crack, and the R, that's what we're interested in, that's the higher one, is perpendicular to the crack. And D is the diameter of the bulb of the tube, or cylinder, sphere or cylinder. The thickness of the bulbs was about 0.01 inch. Homework to do that in millimeter. And the tubes about 0.02 inch. He found that R over square root of C is more or less a constant, 237, 228, 251, 244. Also, he varies the 2C a lot. He also varies the diameter, but R over square root of C turns out to become a constant in his experiments. So he did experiments. And the same he did for the pipes, so circular tubes. He has different diameters, not varying that much. He has crack lengths, sorry. He has different diameters, and then he has calculated the hoop stress per square inch to apply, and found that, or measured them, and found that they have similar values. So 240, 232, 229, so between around 240. You can go through the numbers. So he noticed a constant value in his fracture experiments of glass, namely sigma infinity, the applied stress at infinity, not at the stress concentration, times square root of A or C, yeah, is 2.6 times 10 to 5 Newton per square root of meter to the minus 1.5. Yeah, I just wanted this unit because sigma also is a Newton meter. Right. So, and this is within 5% of error. Or, in other words, more general for material, sigma times square root of A or C is a constant. This is the same table I've shown before. And that's a very important constant, or very important relationship, which we uncover soon in this lesson. So Griffith then looked into the energies, not into the stresses sigma, but he looked into the energy in a reversible thermodynamic energy balance, telling that the total energy equals the mechanical energy and the material energy. So the mechanically applied energy and the energy which is in the material. With mechanical energy is the external workload, WL, plus the strain energy. So I stressed the material, it strains. And we know already in a strain field we put some energy, UE. And we have the material energy, which here we just say this is the US, the free. And now we have to calculate the forces or forces we get by sigma times the area A. So A is the area and B is the breadth. So if I have the crack and I have this in 3 dimensions, yeah, the crack like this, the whole body is in 3 dimensions, then this length here is B. How broad it is, the breadth, the thickness of the material. So 2A times B, this is the area. 2A is that, the crack length, times the width, the deepness, the breadth, we say, is the area A, and we can work it out. So WL becomes 2 times UE, the strain energy, and UE then with the English solution becomes B times sigma square over 2E 2 pi A squared, and US is 4 times A B gamma S. And gamma S we call the specific free and relaxed surface energy. So this is the energy we get when we introduce a free surface per breadth. So that's why we have times B here. So it's a specific per unit area. So we have the total free and relaxed surface energy, and we have the one per unit area, gamma S. So now we look to these different energies. We have the mechanical energy, and we look to the change of energy. So the crack initiation occurs when, basically we have this function here. We have such a function which has a maximum, and there du over dA, it's a function of crack length A. If it becomes horizontal, so the derivative becomes 0, then I get crack initiation. We have these two terms, so U mechanical over dA equals minus sigma squared of 2 pi A, and we have dus over dA, surface energy, equals 4 times gamma S from the formula here. So US and UE. If we plot US 4 times gamma A, means if I increase A, then the surface energy just increases linear with the length of the crack. That makes sense. The breadth remains the same. The mechanical energy, which is sigma squared pi A squared over E, and negative, we have the minus sign, goes down. That means I open the crack, I reduce mechanical energy because part of the stressed material relaxes. So it goes down in this parabola shape. And when I put the two together, so the slope of the down curve is steeper than, not so steep as the slope of the up curve at A equals 0. So the tangent here, that means it first increases with the upper curve, but then the slope of the second curve becomes steeper, so then it goes down, and I get a position A critical where du over dA becomes 0. And that gives me then a critical stress, or critical A, equals square root of 2 gamma S E divided by pi A. You can solve it on A with a given applied stress, or with the given A, you can vary the stress and get critical values for both of them. So this dependence of the strength with floor size A, or C sometimes, was determined for the first time by Griffith in 1921. And there's an important note: when A becomes 0, the Griffith theory doesn't work, because we have a singularity again. So what happens if we make A very, very small? Smaller than the distance of the atoms, you know already, then it becomes discrete theory, not continuum theory. And those continuum equations, they have to be modified. They will fail there. Right, so the crack initiation occurs again when du over dA is 0. And we have u mechanical over dA. I think du should be minus sigma squared over e 2 pi a, and the surface du surface over dA equals 4 gamma s. So because the second derivative, the curvature here, is convex, d square u total over dA square is smaller than 0, and that means this is an unstable equilibrium. If we are at smaller a than a critical, then the crack may close again. If we are at larger a than a critical, then the crack grows. And that means if I have a load control case where the applied stress is constant and I go over this A critical, then I have catastrophic failure. And you can imagine that, because again, you have a lever arm, you have a small lever arm at the beginning, you have to overcome all the surface forces, but then eventually it opens and you get a long lever arm which easily opens the crack tip further. And then you go parabolic down on the energy scale and catastrophic failure. Okay, Obraimov, he did that experiment in 1930. He took this crystal mica. So mica is like, it's a bit like graphite, you may know it, mica, and it cleaves off. So you have lattice planes, they are horizontal, crystal lattice planes, they're all horizontal, a single crystal. And then you can cleave planes off. This is a so-called C-plane. It's a very anisotropic crystal. And what he did, he pushed it up here. This is, I looked up his paper here. So he pushed up part of this cleaved lever arm, little microbeam, by distance delta. And then he looked how far the crack propagates along this direction. Or here we turn it around, the direction in this model. And now the question is, we consider the problem of a cantilever beam. So this is a small cantilever, which again has some breadth B. And in the Euler-Bernoulli beam theory, the boundary condition input is delta. So if we lift it up by constant value delta, then delta is P A to the 3 over 2 E I, and I is the second area moment. I hope you have had that, otherwise you have to look up this theory. As I said, we have to rush through it. And we get eventually the elastic energy equals 1/2 P of delta times delta. Or UE equals, when you work it out, 1/8 EH to the 3 delta squared 1/A to the 3. So what is important here is the 1/A to the 3, because A is a variable. All the others are constant in this given experiment. Here 1/8 is constant, E is constant, H is the thickness, this is given by the experiment, and delta is how much I lifted up, is also given by the experiment. This I just lifted up by delta, not more, not less. And then maybe I start with a crack which is like this. And that means the crack will grow. So it will grow until we show it here. So we have the surface energy goes up with larger A. And we just calculated the UE goes down with larger A, with the third power, 1/A to the 3. All the others are constant. That means, again, I get a minimum here, but this time I have a concave curvature. So it's open to the top. That means du square over dA square is larger than 0, and this is a stable condition. That means if I make my crack longer than AC, it would cost me energy, so it would not grow longer than AC. If I have initial crack shorter than AC, then it opens and opens and opens until it reaches this critical length A. And of course, you can imagine this, right? It makes totally sense. If I lift up a piece and it has the steep angle, then I have a large stress concentration there. Now the A grows, yeah, A, this is A1, this is A2, grows. Then the angle becomes shallower, and I get less stress concentration at the crack tip. And eventually, if it becomes A3 too long, then I create more surface energy than I would gain with the release of stress energy, strain energy, so it would not propagate. Here are some values. Gamma S in air is minus 0.38 joule per square meter, and in vacuum it's minus 5 joule per square meter. So it also depends whether you do it in air or in vacuum. Air can push a little bit into the crack and push the atoms apart. Right. So there are two major cases in fracture. The one is load control, which we show like the figure to the left. This is the unstable crack propagation. Imagine you have this form here. Then when the crack becomes longer, then of course you have a longer lever arm, A, to the crack tip. So you separate you put more torque onto the crack tip. That means the stress becomes higher. Or you have this displacement controlled situation where we can put it in the middle, for example, just for generality. If we displace and keep the displacement like with the lever arm, now it's in the center, then it grows to a certain length and it stops growing. So, fracture. Fracture is important because of these problems, as we show, not just cracking the glass at home or the Christmas balls or other nice things we have, but also big problems. We don't want to have ships or buildings collapse. And that's why it's important to understand fracture. This was, I forgot where it was. In the Griffith theory, we can have the two situations where the far field stress is constant and then we increase A to some A critical. Or we also can say the crack length is constant and we start from zero stress and increase the stress and in stress until we get the critical stress where it starts to, where A starts to move away, to yield. And then what we put in for E. So for E, we put in E star, which is E for the plane stress situation. We have had the plane strain and the plane stress formalisms in two-dimensional formulation. You remember the Airy function. And for E star, we put in E over 1 minus nu squared for the plane strain condition. So this is when we work it out. For plane strain, E is smaller, but E is larger than for plane stress, because nu is smaller than 1, so 1 minus nu squared is smaller than 1. That's in the denominator, so it becomes a larger number than in the plane stress situation. Now Irving came, 1949. He said the critical stress equals square root of E star over pi A times GC. So he put, instead of the gamma, a GC, which is a constant. I come to it, the energy release rate. And at least GC must be larger than 2 times gamma S, or equal. 2 times gamma S, yeah, is the lower limit appropriate for ideal brittle materials. But there can be other contributions. So we have said there's the surface contribution. There also can be a plastic deformation contribution. You can emit phonons, so lattice vibrations into the crystal, into the material, which we call phonons. Or acoustic emission, a mass, a whole spectrum of phonons. And other things. So that all these processes, they cost energy, and therefore Irving replaces this gamma or 2 gamma by what he calls the fracture energy GC. So Irving took the fracture theory one step forward and said, now the total energy is the workload plus the elastic energy plus some material resistance, Wg. So Wg, work load with respect to this G here, the fracture energy. And we say this is some material dependent resistance. So we have a driving force, the mechanical energy has to balance the workload and the elastic energy, and then U or du total over dA has to become 0 for the prop, for the equilibrium condition, or the critical A, and we work it out, dWg over dA equals G. So it becomes a constant G. which we call the strain energy release rate. SERR, SER. You will see that sometimes strain energy release rate. So this is a rate not per time, per unit area of crack advanced, SER, with the unit joule per square meter. And G equals D over dA of the workload minus the elastic energy. So the term rate, as it is used in this context, does not refer to a derivative with respect to time. Often in physics, the term rate is a derivative with respect to time. But here it's different. This is different meaning. G is the rate of change in potential energy with crack area. So with crack area. And since G is obtained from the derivative of a potential, it is also called the crack extension force. If we derive a potential after the area, then become a force. Or the crack driving force. So these are synonyms for strain energy release rate, crack extension force, how much force I need to extend it or to drive the crack. And this was a citation out of that book. The strain energy release rate per unit area, again, I wrote it down here. So if we have a displacement control, that means a fixed grip. Here we apply a stress with constant volume. Volume, the displacement, it's the area times the displacement. The volume is constant. So at constant volume, G becomes then D over dA times U of E. So there's no external workload if we keep the volume constant, right? Nothing happens externally. We can imagine this as shown here from this website fractalmechanics.org, Griffiths. There's a quick geometric interpretation. There's an easy way to remember Griffiths' result, and it is shown in the figure. It is to think of an unloaded portion of material above and below the crack that is triangular, approximately, in nature, having width and a height, P times A. So A times P, half, yeah? This gives an area of pi A squared half, P pi. And since there are two triangles, one on the top and one on the bottom, not shown here, it is pi A squared. Finally, since the thickness is B, so in the third dimension we have the thickness B, the breadth, the volume is B pi A squared, and this matches the volume term in Griffiths' equation. So we have a pi A squared somewhere. So the easy way to think of this is there are a volume of material near the crack equal to B pi A squared that subtract out of the strain energy density sigma squared over 2E, and keep in mind that this is just an easy way to remember the result. It is not meant to imply that the triangular region is in fact a hard boundary separating non-zero strain energy regions from zero strain energy regions. These are continuous variables, continuous fields, as we know. Okay, so we have discussed Irwin's initiation of crack initiation. We have the strain energy release rate, G, which is a property of the geometry and the loading of the material. And then we have the critical G, which is the material property that resists crack initiation. So this is the material constant, and we have this the geometric what we load. And then we have to compare them. And it depends. Sometimes joule per square meter or Newton per meter, same unit. So we can go through all this formalism here, which I let you do as a homework because today's time already is over, but I get a little over. You go through the textbook and we find the load controlled. So again, this situation where we have a constant load, just a weight hanging here across the crack, and the crack propagates, and as it becomes longer, the lever arm becomes longer. So we increase the stress around the crack tip. And then the G equals d over dA WL minus UE equals, so WL is this square, and UE is this triangle here. So we can say it's the opposite triangle, pi. So this energy, volume times stress, or force here in Newton, this gives the energy. So the G is the release of d pi over dA. This big pi here. Pi is WL minus U of E. External workload. And the workload is P times V. So it's this square. V is here, P is there. The square is the workload, P times V. We know that from thermodynamics. So d pi over dA equals dV over dA minus dP over dA times V, which is 0 because we keep P constant, minus du over dA, and that gives us then the stress release rate equals minus d over dA of pi at P equals constant. So the change here. We have the displacement control and we have the load control. I just mentioned the load control. So if I have a crack length A, then this is my pi, the upper triangle here. And now I increase by dA. Then, of course, I change the slope. And I get this d pi, which is minus g dA. And that means that G increases with increasing A. Not so in the displacement control. So on the displacement control, I hold the volume fixed at this value, but I grow my crack from A to dA. And then I have a du over dE becomes minus G times dA, and the G reduces. The G has to reduce to keep the volume constant. So here the G reduces and there the G increases. And that's why there on the left we get at some stage the G reduces under the critical G. The propagation of the crack stops, while under load control it increases and increases, and we know already it increases with the third power of A, of the length of A. Same thing is shown again here. Again, I have to rush. Look it up in the textbook. There's an example. It's the same example what I've just shown in that splitting of the mica, but here you split it to both sides. You split it to the top and to the bottom. So we have the same solution as done before, just a factor of 2, and get the G becomes this equation here. So it goes with a squared. And I let you do that as well as homework. So much about general theories. We have had the Griffith theory, the Irwin theory, and just the ellipse at the very beginning. So far we discussed the energy approach for fracture. Next time I will show you what happens at the near tip stress. So what happens when, on an atomic scale or very close to the crack tip. Have a good time and see you soon. Bye.